Hello everyone. Today we are going to discuss the last part of GIS analysis, that is GIS analysis part 3, in which we are going to discuss buffer analysis, which is very important analysis or analytical tools which are available in GIS. Basically in buffer analysis you can perform this buffer around any vector feature like a point line or polygon, and this is based on the searching, or you give the area that I want to cover this much area, the extent. In case of point data it would be a radius, in case of line data it would be a width, as well as for the polygon data. So, as mentioned here, that the spatial searching based on certain criteria or condition, and it results in the area expansion of the feature and can be visualized as spreading the object spatially by a given distance. Now, this can be given by the user or any attribute which you want to use to create buffer, that is also possible. So, which all these details we will see one by one. These are the examples of 3 vector features having buffer generation, that d becomes the radius. This is the input which a user will give, this is the point data, and a circle is created. We will see little complicated cases when 2 adjacent points are there, that means you can merge the points. Here with the line data also, buffering a line, you provide the width, and around that line buffering can be done. And these things, like in case of point data, why buffering is required sometimes, because there might be a point source pollution, might be a factory or thermal power plant, and you want to assess what is the affected area. So, if you know if you are having knowledge or information that how much area is affected, you can create a circle or a buffer around that point source. In case of a line feature like a road network or a river, if you are having information like what would be the extent of the pollution, and in case of suppose a road has to be widened, then how much land will come under that buffer when you widen the road, that analysis can also be done. Buffer also around a polygon can also be created, like around a building or a agriculture field or a playground, depending on your requirement. In case of point buffers, it is simpler, just the points all along points, a buffer is generated of a given radius. However, if there are 2 close points, then overlapping circles will be created and a merged circles will be there. In case of line, the concept starts like here, that the input feature here is line. What we are having when we give this offset or the width of the buffer, then all along the nodes or internodes circles are created, and important to note here on the edges. On the edges itself also the circles are created, and then these lines are connected, and then a buffer is created. So, that the important point is, from everywhere the perpendicular distance would be the same as per the given width. As I was mentioning about the points, suppose you are having rainfall data, you have given some distance that this much affected information will be there. So, you can create here, you can see when points were very close, then the outer buffers were merged here, like here also. So, buffering techniques in GIS is a good example of infusing extended GIS procedures is in the generating of buffers. Everyone relates to the concept of in the fill distance of a stream, neighborhood, a criteria, habitat area. The concept invokes a circle or a concentric ring around a feature and has a rich heritage in manual map processing. And similarly, the division of a simple buffer into uphill and downhill components can be important. So, if a road is going towards the hill or coming down, then other factors will also come, impediments and other things. So those things can also be involved in. Instead of having a simple buffer, you can create some complicated buffer, but that kind of information is required before you do the buffer. Like a road engineer sees different land slippages considerations in two areas. An environmental scientist concentrate on the downhill portion of the flows of sediments and other chemicals from the road. And in fact, most applications consideration of characteristics and conditions within buffer are at least as important as outline of the extent. So as how buffer works, you can have a fixed distance, and that buffer you give a value that this much buffer in mapping units the value will come, and then buffer is created. And the example is here along a line how the buffer is created through a fixed distance. And buffer or a constant distance buffer can also be created using attributes, like here buffer lines, and you use the attribute which is available in your non-spatial data or attribute table, and you say that along these lines I want the buffer of 10 unit width, along these lines I want buffer of 30 units, and accordingly the outputs can be created. So buffer as distances are dependent on field values, these field values are attribute values, and various buffer width can be applied in the same operation. So these kind of things are useful for certain applications. Now what are the applications of buffers? Buffers can be used to understand the erosional phenomena all along a river or any other natural causes or natural reason, maybe the landslides, earthquakes, how much area got affected, and so on and so forth. Environmental, like in case of pollution, maybe noise pollution, air pollution, point source pollution. In telecommunication, because nowadays lot of mobile towers are coming, and the operators of these mobile towers would like to know that how much area one single tower will cover. So they don't want the gap for the communication, and therefore the buffers are generated, and then one know that you leave one tower goes directly into another tower. So these are the point data, and then point buffers can be created, and having, if there is overlap, then you will not lose the connectivity. So telecommunication companies are also employing buffer techniques of GIS to find out the gaps in their coverage. And power in power generation, especially in hydropower, also the buffering can be very useful. And this is not ending, so this is not exhaustive list, so there will be more applications which are coming now. Another analysis which we can do using digital elevation model, and some certain inputs we have to provide, and that analysis is called visible area or view set analysis, in which you are having basically a terrain which is given here, and the input you provide a offset, and then you would like to know that how much of this slope would be visible from this point, and how much of the slope will not be visible for your point. And the application of such analysis might be when somebody is going for construction of certain things, and then they would like to know that after that say tower comes, then what would be the visible or view set from that tower. Especially it is useful in forest management. It is also useful in case of laying power lines or power towers which for long distances. So if it is these power lines are going through undulated terrain, then one would like to know that where these mountains or hillocks will create the problem, and where exactly the tower should come and not. So for that also the view set analysis can be done. And basically the view set, as I have explained here, that it determines the visibility of an area from a particular or a set of viewpoints. You can have one point, you can have multiple points. and the input layer should contain elevation value. So, the main input here is a digital elevation model, and it is useful for planning locations of surveillance facilities such as fire towers, transmission facilities. Also in nowadays, like if somebody is developing a resort or a hotel in a mountain or a hill station, they would like to know after the when the hotel is constructed, how much what kind of visibility or view set they will have from say top of the hotel or third floor of the hotel or fourth floor windows of the hotel, because you know that this involves the cost and they get in returns, because if from window the view is nice, they can have higher prices for such rooms. So, this kind of analysis are now being done even in the hotel management, especially during the planning stages. So, it has got wide usefulness. Now, on this analytical operations, the last one which I would like to discuss, which has got many sub operations, and that is the connectivity operations. So, what are the connectivity operations which we will see? That connectivity operations estimate values by accumulating them over the area that is being traversed. And the best example can be given that if in a hilly terrain or even on a flat terrain, more you walk, lesser you will walk. That means you are accumulating the tiredness. So, say in first hour you walk 5 kilometers, but in next hour you may not walk 5 kilometers, you may walk just 4 kilometers, and then in third hour you may walk just 3 kilometers or 2 kilometers, because the tiredness is getting accumulated. Similarly, in natural phenomena also, like in sediment transport or in pollution spreading or other thing, these things also there may not be accumulating, but it is spread. But the concept why it is same, that the connectivity operations estimate values by accumulating them over the time, over the area that is being traversed. And to calculate this connectivity function, there are certain inputs which are required, and the first one is they specify the manner in which the spatial elements are interconnected, because this is connectivity function and therefore the interconnections are very much. Second is the rule. What are the rules or constraints you have to provide, the possibilities that control the movement along the spatial elements. And third one is unit of measurement. So, before you go for connectivity functions, these three inputs must be ready, and then you can drive nice results. So, connectivity functions can be grouped into various categories. One is contiguity function, proximity function, in which buffer we have just discussed, Thyssen polygon we have also discussed during interpolation techniques, and nearest feature identification is also possible. Then next function in the connectivity function is the network functions, then spread functions, and then seek functions. So, these functions we will discuss one by one. So, first let us take contiguity function. In contiguity measures which is characterize spatial units that are connected. Everywhere this is connected thing will come. A ground of spatial units that have one or more common characteristics and constitute a unit forms a contiguous area. And then common measures of contiguous are the size of the contiguous area and the shortest and longest straight line distances across the area. We will see some examples here also. So, in contiguity functions, like here we are having one input map is here, which is a land cover map or land use map, and there are certain features which are present, like forest is here and then swampy area is there. Now, what we can put in contiguity function, we can put certain conditions and then input that what we are looking, that determine land units to be used as nature reserves, which should include forest, and river network is also there, which should include forest, include rivers and swamps under the condition that the minimum area should be more than 400 square kilometer and no section narrower than 10 kilometer. So, these are the constraints and these are the inputs through a land cover map. Once you use the contiguity function and then put all these constraints and inputs, you get this area. So here these are the areas that these areas are including forest, are including swamp, and they are having area, minimum area is 400 square kilometer, and no section is narrower than 10 kilometer. So likewise you can get the output from that. So depending on your requirements, you will choose a appropriate tool, bring the inputs, bring the constraints, and then perform the analysis. Now in next function of connectivity function is the proximity functions. That proximity involves the measurement. Unit can be distance in length, travel distance in time, or other units. And to calculate this, again like in contiguity function, again here also you require certain inputs. What are the inputs? That objects. Input may be a map of roads, road network, maybe a groundwater well, maybe a thematic units. And unit of measurements, that whether these you want results in meters or seconds or whatever, because time may be involved here. A function to calculate proximity. How this proximity will be calculated? For example, maybe a distance, and then the area of interest should be specified, whether you want to perform on an entire input map or in a small part of the input map. So when you go for that, like examples are determination of buffer zones along groundwater exploration wells, construction of Thyssen polygons all along this rainfall stations, or determination of accessibility to drinking wells. So these will fall in the proximity analysis. And this is how the distance is calculated, because distance is, as you can recall here, that the function to calculate distance, calculate proximity, that is distance. So this example here is that this is the input map, whereas the S stands for source and the question mark is for undefined, where we will calculate the distance. And again it is based on roving window, which we have discussed in earlier part of GIS analysis, that here for central pixel the value has to be calculated, and these are the weights which have been assigned. So if the central pixel is undefined and one of the neighbors is not, then apply the filter iteratively, and one by one then throughout this thing it is applied, and in the center you get this one. So distance is in meter, because this is the source. So that is why distance here is coming 0. As you go away from the source, the distance increases. When you go diagonally, accordingly the distance has been calculated. You go up and down or east west, the distance is calculated. So this is how the distances are calculated in proximity analysis. That is the function. This is the function which is involved here. In proximity analysis, like a buffer is one of the example, that initially the road was say single lane or double lane. Now it has been decided to make it 4 lane. So there will be few inputs. One is that how much width is required for 4 lane, that input has to come, and then existing road network is there, and then land records, or also which are also called parcels, land records through revenue department has to come, that map. So now once the buffer has been created all along that existing road, now exactly you know that how much whose land and how much of their land will go under the road, and accordingly then permissions and compensations and other things can be provided. Similar example I can give, that like there is a mineralization zone or along a line or in a linear fashion. Now if you want to, if the government is deciding to give on the lease, so they want to know that if mining is done, then how much area has to give in for the lease. So once along that mineralization a buffer is created depending about the the requirements for the mining, and then whose land will go in that lease can be determined if you are having the revenue records. And once that is there, now exactly you know to whom the money has to be given, how much, and so on and so forth. So it has got really good applications. There is also proximity analysis can also be used for accessibility mapping, and here there is a water well for which the water has to be fetched, and there is a road network, there is a bushy area, the fields, agriculture fields are there, and swamp is there, and river is also there. So all these, this is a typical land use scenario. Now in accessibility or this proximity analysis, there are certain rules that road, the speed along the road is going to be 2 km per hour, whereas the speed along the field is going to be 1 km per hour, and if one has to walk through the bush area, then it is 0.7 km per hour. And also the conditions have been declared that along the swamp and river no walking is possible. So these are inaccessible area, and of course unit of measurement here is time. So once these are the constraints and input map is available, then this is the map which has been created, which tells that within this the black area, this is within 30 minutes the water well can be reached. One can reach to this water well within 30 minutes if he is present within this black area or this black polygon. Then in grey polygon, this is 60 minutes, and then it is 90 minutes. Since this is the swampy area, and we have set the condition that swamp is inaccessible, and therefore this has been excluded in the analysis. So depending on your requirements, and once the rules constraints are available, one can do all different varieties of analysis using these functions. Now the another the connectivity function is the network function. You remember that initially the development of GIS or invention of GIS started for network, and therefore GIS is extensively used till today for network related things. And initially the software were also very powerful, mainly for network analysis, but now at the same time they are also having equal strength for raster data analysis. So in network system, which are connected linear features through which resources flow or communication is achieved. Resources flow, that might be a river, a natural river system. So resources might be water, resources might be sediments, or maybe pollutants. And then also communication, maybe it is a road network or a power grid or a sewerage network, and so on and so forth. So this is also what the resource might be movement of people, transportation, distribution services, allocation, delivery of resources occurs through a network system. And the movement along the lines is affected by other elements and their characteristics in the network. If resources have to move through a say road network, then one need to know whether it's a two-way or single way, or single lane or two lane. These kind of constraints on information are very much required. And then of course traffic conditions, red light zones and crossings and flyovers, that all kinds of information will be required to achieve a very good network analysis. Let us see what are the other details which will be required. The network functions are commonly used in analysis that requires moving resources from one location to another, and GIS is used to perform network analysis such as prediction of network loading. And this is basically the determination of shortest path between connected points or nodes within the network based on attribute values. And this is often referred as the route optimization. This is nowadays being used extensively by even fleet of taxi operators, maybe other transport systems, maybe by the emergency services like fire brigade or ambulances, maybe by police. So attributes values may be as simple as a minimal distance or more complex, involving a model using several attributes defining rate of flow and cost. We will see very shortly the examples, and like route alignment, optimal path, shortest path identification, allocation problems, and then distribution problems are there. So, in network analysis, the facilities management based on network analysis, and specific areas of application could be determined optimal and shortest path as routing analysis or allocation resources, and based on set of connected linear features, because for network analysis the input is there has to be one network, whether it is a road network or a stream network, a river network, or maybe network of electricity, telephone lines, sewerage line, all kinds of networks. That one network at least, or maybe two depending on the analysis, will be required as one of the inputs. So, in the network analysis, 4 components are usually considered, the inputs. The first one is a set of resources. For example, sediment transported by the water along a natural fluvial system or river network, location of resources, a fluvial system for example, a destination, that is the outlet of the water set. And then fourth is the rules, constraints, conditions, a set of constraints, for example in this case that only permanent streams of higher order. You know that in stream ordering there are different ordering system exists. So, when a stream basically starts, that we consider as first order, then 2 streams meets, generally in one scheme we consider second order, and so on and so forth. So, higher order means that we are going for not first order, second order, maybe 5, 6 order streams here. So, these are the 4 inputs, a set of resources, a network, location of resources from where the resource will start moving, a destination where it will come out, and then how it will move. The set of constraints have to be provided. Now, examples are transport of sediments in a fluvial system, route optimization such as airline scheduling, maybe urban transportation services, subdivisions of municipal district into the zones which can be served by the hospitals, schools, emergency services, and subdivisions of a forested into zones that can be effectively covered by fire brigade in case of emergency. These are the things which are very much required in case of forest fires and other things. So, this will definitely help, network analysis will help to manage forest fires whenever they occur. Now, the another function, the second last function is the spread functions. Spread functions, as you can name implies, that the spread functions evaluate phenomena that is spread, dilute or accumulate with the distance, and distance can be expressed in unit of length, travel time and cost. And the spread functions have characteristics of a mix of proximity and network functions, and a spread function evaluate phenomena that accumulate with distance, and these are used to calculate transportation time or cost over a complex surface, and the estimation of time taken to walk in a relatively rugged terrain. As earlier mentioned, that more you walk, the longer it takes to walk over similar terrains. That means when you walk on a terrain, after some time you accumulate the tiredness, and therefore you would walk less. So, this is considered in a spread function. Spread function can also be used in case of flooding. Spread function can also be used in case of simulation of reservoirs and other things. That example we will see soon. And this is a consequence of the cumulative efforts over the time, the spread function, and a topographic incline impedes movement differently in uphill, downhill or across. When you want to go for real type of analysis, and if it has the the terrain is undulating, then you can also add this impediments here. And the spread function is also applicable for estimation of mine outputs. As you know that the mine, whether it is an open cast mine or underground mine gets deeper, the output reduces. So, if you want to maintain the output, or if you want the constant output, then you have to bring more resources to keep the constant output, because the distance and cost is accumulating, and therefore you have to bring resources in order to have a constant output. And similarly, the pollution plumes in air, surface and subsurface. This is a spread function, but in opposite sense because this pollution plumes will spread in air and the concentration reduces. It does not accumulate, but it reduces. Same would be if it is a fluid, and then it will flow on the surface or maybe in underground conditions. So, those things can also be estimated, that how much time it would take to reach the pollutants at that particular distance, whether it is air on surface or in subsurface condition, and what would be the concentration as well. But before that, you require, if somebody is estimating this pollutants movement in subsurface conditions, then lot of other inputs would be required, that what is the conductivity of rocks which are present in subsurface, what are the structures are there, and so on and so forth. Now, these typical examples of spread function, as I also mentioned, the determination of inundated area due to a dam construction or a reservoir construction, determination of flooded area due to dike work. Sometimes in order to protect flooding, embankments or dikes are constructed, but when a lot of water comes, sometimes these dikes may breach. So, you want to predict that what would happen if a dike breaks, like along the Kosi river, such embankments have been created. Sometimes we hear that due to flooding, these dikes have breached and the new areas have got inundated. But using GIS, we can predict, we can see that what will happen. Spreading of pollution is also an example, and also during planning or construction of canal, which is relatively related to accumulation of cost. With every meter by which the construction of canal proceeds, cost accumulates, because the length is increasing, and once the length is increasing, more resources would be required. That means more cost. Let us see the example of a spread function for in reservoir simulation or dam simulation. In the background, you can have a digital elevation model in your GIS software. You can create a dam axis by giving a height of the dam or the water level, and then you want to see that how much area will be inundated in the upstream. Like in this example, the water, this is the digital elevation model shown here in form of contours. Water level is plus 290 meter, that means above the ground, and here this along this dam axis, and then once you go for this spread function or some other tools which are available like profile extractor, or you can also use cut and fill tool, especially the fill tool, and this will estimate that how much volume of water will be stored above in upstream from once if this reservoir comes or come in existence, and the total area which will get inundated in upstream area, that can be. But suppose you are looking for more volume of water, that too can be simulated, that I want more volume of water. So, you have to raise the height of this dam. So, instead of now 290 meter, if I raise by 5 more meter, that it becomes 295, then more an area will be inundated, and then you are having higher volume of water which is available in the upstream area, and of course larger area will get inundated. Nothing is being done on the ground yet, no cost is involved, except on your GIS platform you are doing simulations. If you are not happy with this, even this volume, you can change the location of this reservoir or dam axis. You can go little downstream, then start simulating again, and once you achieve the required volume, then you finalize. Another thing is, in this particular example, this dam simulation is shown that dam axis has to be straight, need not to be. You can have even like curved shape, or having a some angle between two sections of a polyline. And there too also a dam simulation can be done. And also you can rotate once you have drawn a line for dam axis, you want to change the orientation of that one or shift that one. All these things are possible. Once you have decided now it is final location, this is the thing, you assign the height, then simulate the inundation. So it is very, very useful, and not only for planning at the planning stage or feasibility stage of a reservoir, but also these things are useful in case of groundwater recharge, because you can assess that how much existing reservoir is providing groundwater recharge, which you may assess through the growth of vegetation. So if in that area if the similar size of reservoir comes, you know before really a reservoir is coming that this much area, because you have already got the knowledge from existing reservoirs, that this much area will be benefited from groundwater recharge. So spread function, especially the dam simulation or reservoir simulation, is very, very useful for many applications. This is the example of dikes, that areas here, this is the the area above mean sea level. This is a typical example of a part of Bangladesh, and there you are having that the ground level or ground or land part is just a few meters higher than the sea. So if a dike fails, then this is the scenario which you are going to have, rather than spreading everywhere, which may not be true. So once you have decided for this dike failure, they like in case of reservoir you have to have a reservoir. Similarly in case of dike failure, that feature will come as an input. Once that information is there, you can simulate, and you would know before really anything happens that what would be the volume of water will be there and how much area will get affected. This is m power 3 and m power 2. Now the last function in this connectivity analysis is the seek function. This is another very, very useful function which you can use along with a digital elevation model and some other modeling tools like surface hydrologic modeling, which I will discuss soon. So seek functions determine optimum pathways using one or more specified decision rules, and this the process is repeated till one or more decision rules becomes inapplicable. And the typical examples or determination of path of water flow, highway planning. We will be seeing the first in little detail. That input here is digital elevation model shown here as in form of contours. When we go for surface hydrologic modeling, we can drive automatic flow path that how the water will flow. So this is a seek function, and how it is being determined, as you can see that the process is repeated till one or more decision rules becomes applicable. So this is based on decision rules. Decision rules will come through the surface hydrologic modeling concept. The input is digital elevation model, you decide, and then you can create automatically the drainage network. You can also create the watershed boundaries. You can also create this stream ordering and so on and so forth using hydrologic modeling and using seek functions. So this brings the end of third part of GIS analysis. Thank you very much.